Hello and welcome to our webinar today. Over the next 20 minutes, I'd like to introduce you to how Autodesk are addressing our customers' key business challenges through simulation early in the design process, and how we're breaking down the barriers to a broader simulation adoption. My name is David Hick and I head up the European technical team for simulation at Autodesk. Over the past 10 years, I've been helping manufacturing and construction companies throughout Europe gain a competitive advantage through the implementation of simulation tools within their design process. So to start, let us take a look at why companies perform simulation. They perform simulations to validate their designs, to ensure they perform as expected in a real-world environment. Secondly, to optimize designs, to see the effects of geometric changes or changes in materials, or the effect of trade-offs, for example, strength and weight. And finally, to reduce the reliance on physical testing, or to test their products in an environment in which they cannot test physically, for example, under extreme heat or very high pressures. Now, these reasons, however, come down to business pressures. Increasingly, HVAC suppliers are seeing a need for improved performance and quality in their products in order to compete. Much of this is motivated by energy efficiency targets set by building owners, with standards like LEED, BREEAM and Net Zero prompting innovative new ventilation strategies and the use of new technology. HVAC suppliers need not only meet increasingly stringent performance specifications, but they must also prove that their products will perform over the long term in complex, large-scale environments. At the same time, pressures from shorter project cycles and reduced construction budgets are dictating faster turnaround times and lower development costs. All of this means that opportunities for design exploration and optimization using traditional prototyping methods becomes limited. Now more than ever, HVAC suppliers must balance client demands for higher performance products and faster product development in order to remain competitive. Typically, the key pressures are shortened development schedules and reduced costs. In this table, we can see how simulation can address these challenges. 6.9 represents the average number of prototypes created and tested during a typical product development cycle. On average, companies that implemented simulation on low complexity products saw a 33-day time and €14,000 cost saving. When we now look at very high complexity products, companies on average see a 253-day or €2.3 million cost saving. These savings are somewhat conservative as they represent simulation in general. The feedback from our customers is that they're seeing even greater savings with our products, with up to a 65% reduction in cost as opposed to 37%. So let's see how the product development process would evolve if we made the change to simulation. If we take a look at a typical product development process going from conceptualization all the way through to manufacturing and implementation, what we know is that the ability to implement a design change which will improve product performance actually declines over time. The reason for this is because the cost of each change goes up as more and more constraints are placed on the product and a high level of detail is incorporated into the drawings. Now, the traditional design process concentrates the bulk of the development effort at the testing stage. Here, physical prototypes are often used for testing and validating the product prior to advancing to the manufacturing stage. So here we can see our 6.9 prototypes. As you can imagine, if the product requires more physical testing, more prototypes, it runs the risk of going to market late. If too few prototypes are tested, the product could go to market and there could be quality or reliability issues. What we are now seeing is more and more design teams exploring design changes earlier in the development process through the use of simulation, where they can look at a wider variety of design options faster and at a lower cost than they can with physical prototyping. So, we've talked about the benefits of making the change to simulation. So what are the risks if we don't? Many companies find it hard to change their product development process. The risk of doing so can seem too high. However, the fact is the risks are far greater if they don't make the change. So what happens if a company doesn't truly know how its products will perform as they go to market? Well, in a worst case situation, a product is released and a recall is needed to correct the situation. So these recalls are not only costly, but of course they can affect the company's reputation. So who uses simulation tools? Well, the answer to that is simple. Any company that designs has a development cycle that can be impacted by simulation. Whether they're designing lighting systems for vehicles, industrial machinery, or buildings with greater sustainability, or the next innovation in clean energy products. In all of these application areas, these companies have a need to remain competitive in their markets, and so they need to have a thorough understanding of how their designs will perform well before they exist in the real world. So to address this need, Autodesk has spent over $500 million in building a world-class portfolio of proven simulation technology. So with our current simulation portfolio, we're helping our customers solve real-world design challenges related to the structural integrity of their building designs, the manufacture of the plastic molded parts, the mechanical performance of their products, and the airflow and heat management of their products within a built space. These products provide the most comprehensive set of simulation and analysis tools available on the market today. So let's take a look at some of the key challenges that each of these products are helping our customers to address. So Simulation Mold Flow enables designers and engineers to assess the manufacturability of their plastic injection molded part designs. They can optimize plastic part and mold designs to ensure that the molds will work right first time round, helping to avoid costly production delays and mold rework. They can assess whether the parts will fill correctly, whether there will be any defects which could affect the part both aesthetically and structurally, for example warpage of the molded fan or blemishes and sink marks on a thermostat housing. On the actual processing side, the cycle time, temperature and pressure can be optimized for cost and quality. The capabilities available through Autodesk Simulation Mechanical provide the broadest platform of structural simulations available to address all of these challenges, expanding significantly on the capabilities currently available within Product Design Suite Ultimates. So whether an engineer is looking to determine the location of stresses in ductwork hangers that could cause failure, the level of deflection or even permanent deformation, the fatigue life due to cyclic loadings, the effects of a drop test of a roof-mounted unit, or how vibration frequencies affect the structural integrity of a piping system or ducting, identifying structural redundancy and alternative materials for weight savings and cost savings. Simulation Mechanical has the capabilities to address all of these common nonlinear applications and more. Structural engineers are always looking to determine if their designs satisfy all of the applicable code requirements from strength to serviceability. Robot Structural Analysis provides them with these answers. Robot Structural works with any material and has key design codes built in from around the world for today's global market. Results are provided based on least weight or other criteria, allowing engineers to give their input into a project-wide sustainability assessment. Complicated analyses such as seismic or footfall studies can be conducted and results can be downloaded and incorporated into the CAD model for visualization and code checking. But the biggest growth area in simulation at the moment is in the field of CFD. Autodesk Simulation CFD provides designers and engineers with a broad range of analysis capabilities to address all of these common fluid flow and thermal related design challenges, such as determining ways to increase the flow throughput in a device, or identifying the cause of pressure losses in products, ensuring that the flow is balanced through a system, identifying whether components will get too hot or what happens when thermal loads or pressures are cycled over time. Will the occupants in a room space be too warm or cold, and can they clearly see the exit signs in the event of a fire? What is the most effective ventilation strategy in the room? Will the room be in sun or shadow at different times of day? And how warm will the room get as a result? Again, all of these challenges and more can be addressed with Autodesk Simulation CFD. In addition, there's interoperability between the simulation products. So, for example, if a designer wanted to assess the thermal or pressure outputs from Simulation CFD on the structural integrity of their parts, then they can do with Simulation Mechanical. Autodesk Simulation CFD can be used in many different ways, as a digital flow bench, a digital wind tunnel, a thermal test rig, or even as a virtual building. And the HVAC products within the building services industry that can benefit from Autodesk Simulation CFD are equally as varied. From assessing the flow balance through ducting, the air profile and throw from a ceiling diffuser, the hydraulic efficiency and flow rates from a new fan design, the desired comfort temperature from a convection heater or an air conditioning unit. More and more often we're seeing manufacturers of these products using Simulation CFD not only to understand and improve the performance of these products in a test environment, but also to simulate their products performing in their client or customer's virtual environments as well. Simulation CFD is also being widely used by architects, designers and engineers involved in all areas of building and building services design. Users can simply and effectively simulate the effects of ventilation, both forced and natural, to establish indoor air quality, look at the effect of temperature variations from people and equipment, and how the ventilation system design can provide an acceptable occupant comfort level, right through to the effects of wind loads on externally mounted equipment. So why have more companies not made the investment in simulation? Well, traditionally, there have been barriers to the broader adoption of simulation, and it really comes down to three key points. Firstly, ease of use. Simulation has traditionally been perceived as difficult, requiring specialist qualifications, training and knowledge, and often not seen as being integrated within the product development process due to an inability to integrate with existing design workflows. Secondly, the massive amount of computing power and time that historical approaches to simulation has required. And finally, the overall cost, the total cost, so the cost of hardware, software licensing, ongoing maintenance costs, training, etc. These barriers have prevented many companies from undertaking simulation at all. In some cases, companies have relied upon third parties for subcontracting the most critical aspects of their product development for simulation, or at best have limited simulation to a minority of people within the company who are able to adopt these tools. So let's take a look at what makes Autodesk simulation different and how we're looking to break down these barriers. Well, firstly, we recognize that different people have different requirements and can benefit from simulation in different ways and at different times in the product development process. So our view is that everybody involved in the development process needs to be involved in understanding the impact of their design decisions. So it's clear that the needs of the designer, engineer or analyst are very different. Now, the historical answer to this challenge has been to try and take an analyst level solution and dumb it down for different users or for use by different people. And this has never really worked. It's simply solidified the perception that simulation is difficult to use. So here at Autodesk, we're taking a clean slate approach to this problem by providing simulation tools that are suited to each of these individuals. So in the case of our Simulation CFD product, this has been developed for use by designers, engineers and other non-specialists. Simulation CFD is CAD-driven, whether that CAD be an Autodesk CAD product such as Inventor or Revit or another third-party CAD modeling system, with a high level of automation to enable the user to focus on getting rapidly to the results. It's accurate, easy to use, and designed for the infrequent user with just one day of training, and features a broad range of analysis capabilities, as we've already seen. Now, typically, the biggest barriers are hardware and cost. Today's simulation tools are expensive and largely out of reach for the majority of designers and engineers. Often the varied requirements for simulation on a day-to-day or project-by-project basis can make it hard to justify the investment. So we'd like to introduce you to Simulation 360, and this is revolutionizing the way in which our customers can access and perform simulation. With this, we're taking all the benefits of simulation-driven design on the desktop and then providing easy access to the infinite computing power of the cloud. By moving the computationally intensive tasks to the cloud, such as meshing and solving, our customers can eliminate the need to purchase dedicated, expensive hardware to run their simulations. The user simply installs a lightweight client on any machine they choose to use, and access is then provided through a user account. This approach provides a flexibility of access to a broad simulation portfolio of capabilities, but on a cost-effective, pay-as-you-compute model. Now, one of the major benefits of using the Autodesk Cloud for simulation is that a design engineer can test multiple different design variants under all possible test conditions in parallel rather than sequentially. This opens up a whole new approach to product development, whereby engineers can now run unlimited analyses at the same time to get the best answer rather than just a single answer. So in other words, they can now fully optimize their designs, perform design of experiments, or try to innovate new approaches to solving their design challenges. The net result is a further reduction in development cycle time and cost, further improved product performance and reliability, and greater confidence in their final designs than can be achieved through desktop simulation alone. Multiple projects can be run simultaneously to ensure that all projects are kept on schedule without the need to prioritize. It also enables larger and more complex models to be run than ever before. So let's take a look at the steps in using the cloud. So first of all, the user simply downloads a thin client installation, and the access is provided with a user account through Autodesk 360. The user then opens the CAD model into the simulation product, defines the parameters for the simulation, and the model is then automatically uploaded to the cloud for meshing and solving. Results are automatically streamed back to the client, or the user can disconnect and reconnect at a later date to view the results. A simple utility, as we see here, enables the user to track the progress of the simulation while it is running, with the option of storing results on the cloud to enable collaboration with other team members via a tablet or other mobile device. So often there are questions arising around security from the cloud. So firstly, let's take a look at informational security. So as the user logs into the Autodesk 360 accounts, the login name and password verifies their access. Secondly, secure standardized IP protocols are utilized for encryption for both upload and download of the data. Now, these are the same protocols which are used for internet banking and e-commerce companies that we use regularly at home and at work. In addition, no customer data is actually stored on the cloud unless the customer would choose to store it on the cloud or a third-party service. Another key point to mention here is often the data being sent to the cloud is low in IP or intellectual property. And of course, many of the models which are uploaded to the cloud are typically conceptual models. Secondly, there is physical security. This is data protection at the server site, protection against theft, fire and flood and so on, and of course operational security too. All of these are expensive investments and are rarely replicated with many in-house IT infrastructures that we see at our customer sites. So let's now take a look at a few examples of where our customers have solved their design and business challenges through the implementation of simulation CFD. Our first example comes from the healthcare industry. In the US, it is estimated that there are over 1.7 million total infections each year in the US alone contracted from hospitals. In addition, there are 99,000 patient deaths each year in the US due to these secondary infections contracted from hospitals. And this is costing the US healthcare system heavily as a result of additional care and lawsuits. A study was conducted that determined that the primary cause of these secondary infections were due to debris and contaminants being drawn up off the floor of the operating room and deposited onto the operating table. This was caused by the way in which the air in the room was circulated originally. Now, Huntair is a leading airflow management company based in the US. The Clean Suite air delivery systems are designed for critical facilities like hospital operating rooms, where precise control of airflow is needed to ensure air quality and mitigate the risk of infection. Huntair custom designs each Clean Suite system to match its specific application. They integrate the air delivery system into the equipment required for each room, and due to the uniqueness of each room, it is often impractical or impossible to physically test their equipment in these configurations prior to construction. So using a digital CFD model allows them to study flow patterns, recirculation zones, and thermal phenomena present in these rooms early in the design process without investing time in building full-scale physical mock-ups or trying to adjust the design in the actual room, which would result in significant downtime for the facility. Airflow patterns can be visualized and the local mean age results displayed to show the amount of time air particles have resided within the space. And this, of course, serves as an indicator of stagnation, recirculation, and potential contamination zones. The impact of thermal plumes above heat dissipators can be explored by reviewing temperature results. And here we can see in this image airflow traces showing a lot of recirculation of air around the operating table. The design of several configurations allows comparison of airflow patterns and provides an understanding of the sensitivity to various inputs and conditions. In this case, 8 different types of diffusers and supply velocities were explored, helping to identify the impact of moving from the minimum standard array recommended by ASHRAE guidelines to Huntair's own high-performance Clean Suite array. Here we can clearly see the difference in the optimum air delivery system, where there is no recirculation whatsoever around the operating table. Visualizations can be output as static images or videos, as we see here, to share results with prospective clients, demonstrating the merits of the proposed approach and giving the supplier a competitive edge, particularly during the bidding process, to help them win more business. Our next example is the VentFS system developed by Green Structures and is essentially a passive heat exchanger ventilation system designed for easy home retrofits to increase ventilation while passively lowering heating requirements by preheating incoming air, saving energy costs and therefore reducing carbon emissions. And retrofits are important in the UK, where a third of our buildings are over 100 years old. And with the UK government aiming for an 80% reduction in emissions by 2050, coupled with the fact that 45% of all energy consumption in the UK is by buildings, then this presents a significant challenge in the building industry. Ventilation not only keeps occupants cool in summer, but also prevents the build-up of carbon dioxide and other VOCs and other naturally occurring pollutants. Clean air ventilation is also important in winter. However, the cold clean air is often heated in the house, which is costly and increases carbon dioxide emissions. Now, the existing solution to this challenge is the use of mechanical heat recovery ventilation systems, which heat the cool incoming air with warm outgoing air via a heat exchanger. Now, while these systems work, they're large, costly to buy and maintain, and also, of course, they use energy to run. Now, the Green Structures alternative takes advantage of existing chimney and fireplace systems. The chimney would contain an inner and outer tube whereby the warm stale air would rise up through the inner tube to be replaced by cool external air being drawn down through the outside tube. The tube system therefore acts as a form of heat exchanger. Openings within the house would also help drive this effect, as inlets are installed at the base of fireplaces and outlets at the top of chimney breasts. To optimise the airflow through the system, due to wind, a cowling was designed at the top of the chimney which works in a similar manner to an airplane wing. With speeds lower than 1.5 metres per second, the cowling draws in air using the Coanda effect. The rate of airflow through the system then increases with an increase in wind speed until at high winds the cowling throttles the airflow. Autodesk Simulation 360 was used to assess over 200 digital prototypes created and modified in Inventor to minimise the pressure drop through the tube system and therefore maximise the flow throughput, whilst also achieving the optimum surface area for heat exchange permissible within the manufacturing cost constraints. The net result is a design with 90% efficient heat exchange, so that for a 10-degree differential between inside and outside temperature, the incoming air would only be 1 degree cooler than the air already inside the building. Our final example is from a leader in providing products for fire safety, comfort ventilation and industrial ventilation. Here we see a new concept for a roof hood, which is designed to enable the exhaust of stale air from a building by way of an air handling system, whilst at the same time avoiding the ingress of rainwater. The design team here would develop a prototype which would be tested under various different pressure conditions in order to develop the performance curves that we see here. If the product fails to meet the expected performance, then a redesign is required, followed by further expensive and time-consuming testing until the product performs as expected. Autodesk Simulation CFD enables engineers with no previous knowledge of CFD to use their desktop PCs as a virtual test bench. Engineers are able to gain a full understanding of the airflow characteristics through the product in a way which is not possible on a test rig. Here we can see some sample results for the roof hood model. We can see a simple cross-section view through the roof hood showing the airspeed as it passes through the duct and around the drain plate, enabling the engineer to see clearly areas where the air is stationary or moving at a very high speed. The engineer can then dig in further and look at the direction of the airflow at any location. Areas of recirculation or flow reversal can be easily identified, and by looking at the pressure profile, the engineer can measure the pressure drop through the roof hood and identify areas where the design can be improved to limit losses. With this insight, the engineers can then develop a working solution. Different design configurations can be rapidly investigated and their performance merits compared at the earliest opportunity in the design process, therefore ensuring that the final product performs as required. Let's take a look at some of the extended capabilities for SimCFD in the HVAC space. Firstly, fans. Fans are the driving force behind the ventilation in most built environments. These products are usually tested in large, expensive rigs whereby the downstream pressure can be regulated and the effective air throughput and torque measured to develop a fan performance and efficiency curve. In the past, empirical data has been relied upon for the development of fans. However, the emphasis on increased product performance and efficiency and the need to use cheaper materials and fewer parts, coupled with lengthy testing cycles, is providing a significant challenge for the manufacturers of these products. With Autodesk Simulation CFD, the designer can simulate the airflow being driven through the fan by the rotation of the impeller. The designer can then look to measure the variation in flow rates as the pressure is varied in order to develop the performance and efficiency curves. At the same time, the designer can gain insight into how the fan behaves, not just in a test rig, but in a particular installation and how it interacts with the surrounding ducting and enclosures. The design of the fan blades and enclosures can be optimized to ensure a smooth delivery of air with a minimum of loss and the minimum of noise. Air conditioning systems are constructed from a series of individual component products, including compressors, fans, pumps, heat exchangers, valves, filters, all housed within an enclosure. Individually, each of these products can benefit from Autodesk Simulation CFD, whether to ensure that the pump delivers the refrigerants at the correct flow rate with the least amount of power, or to ensure that the dynamic performance of the valve is achieved with the minimum amount of mechanical wear. The air conditioning supplier would then look to configure these components into an enclosure. Again, Autodesk Simulation CFD can provide the system-level designer with the insight to ensure that the fans are sited correctly to provide an even flow coverage over the heat exchanger and that the heat generated by the system is adequately managed. So, let's now take a look at our offer. We're providing two packages. Firstly, Simulation 360 Pro, which includes the cloud versions of Autodesk Simulation Mechanical, Robot Structural Analysis, and Autodesk Simulation CFD on a one-year term base from just €3,950. Our Sim 360 Moldflow package builds on this with the addition of the cloud version of Moldflow Insight. These products are of course available as standalone desktop products which can be purchased a la carte. So, I would like to take this opportunity to invite you to take the next step and discuss with us directly your challenges. Please feel free to contact me via the email address shown here if you'd like to learn more about our Autodesk Simulation products. And we thank you for your time.